Okay, good morning. Can anyone hear me? Can anyone hear my voice?
Yes.
Okay, thanks. Okay, let's continue. I think last Monday, right? Monday we discussed about the multiple variable optimizations with the inequality constraint, and the only example I show you is this one example to show how we handle with the case where there are many variables in your optimization problems. And with that, or with those variables, we also have some constraint, which is not just normally we prefer to have equality constraint, but if we have inequality constraint, this is a quite big difference. And I think the idea behind just to provide the slack variable, and you will end up with the Kuhn-Tucker, what they call is Kuhn-Tucker conditions, right? Like this. And with the Kuhn-Tucker conditions, the thing is look like the same with the equality constraint case or situation where you have the Lagrange multiplier with you, and you have to check what they call the border limitations and etc. Right? Whether to that optimality is the minimum or the maximum. However, you see, in the Kuhn-Tucker conditions, the difference is you have the some cases to be considered. Like we have to classify the your problems into many cases. In this case, we have case A, case B, case C, and case D. So it's, the number of cases is depend on the inequality constraint equation you have, right? Since mainly you see is the number. The cases depend on the number of beta and the number of the G functions. So if you have the two function of the inequality constraint, say you have G1 and G2, you have to have the beta 1 and beta 2 as your associated Lagrange multipliers, and that will create about 4 cases for you, right? A, B, C, D. Imagine if you have in total three three inequality constraints in your problems. The case gonna be larger, right? It's gonna be a case where you have zero, all zero beta, all zero G, uh, some beta zero, some G equal to zero. So the case is maybe not 4, maybe 6, maybe 8. So it depends on the number of the inequality constraint you have. But the standard optimization condition, I mean the necessary conditions, quite the same as the case of, look at this one. The condition of the standard, I would say necessary condition is look rather the same. Right? You have to set the things like in the green rectangular, the term like that need to be set to be zero. And from that, you can get the stationary points. And you have to satisfy also case A, B, C, D, right? Uh, in this example, if we closely look at the result we obtain, I would like to go one by one to make it more clear to all of you, maybe. Let's see, for example, case A, we start with using the green. We start with beta 1 and beta 2 zero. This is case A of mine, right? Since we introduce this one, into the necessary conditions, what we have is we have the x1 and x2 as the result. We have g1, g2, and the f is just we evaluate the area, right? And we found the area is zero. F is zero on the last column, as you can see. So this is the trivial case. We conclude like that. Look at case B. In this case, I think we start with this. We set beta 1 and G2 become zeros. And with these given conditions for beta 1 and G2 be zero, we can obtain x1, x2, beta 2, G1 as the result. And you see the number we obtain here, there's some thing that violate the conditions we must satisfy. For example, I would draw the lead for you. In case of, you see, the first one, x1, x2 is good. X1, x2 seem good to me. It's positive, right? Both of them. We consider the number in the first quadrant only. Therefore, x1 and x2 need to be positive number. So I'm fine with these two values. How about the beta 1? Beta 1, it get positive 1. Never mind, right? For the beta 1, maybe we discuss about the beta later, but beta you can obtain plus and minus and zero, no problem. And G2, you see G2 is something, a number is like a 8.89. This is not good, right? This is not good. It's not good because what? Because the condition we have here, the G1 and G2, both of them need to be less than zero. You look at G1 functions. This is an inequality constraint. And we set everything to the left-hand side and left zero on the right-hand side and make the sign to be less than and equals. Therefore, our G1 always need to be zero or less than zero, right? So it could be negative number. However, in this case, it looks like my G1 contain return the positive number 8.89 is not allowed by these equations. Therefore, I think this one is not good. So you have to remove this one, right? It's violate your conditions. The second case of B, you see second, third, and fourth, all of them has a problem of this, of x1 and x2. Since we consider only the first quadrant, therefore we don't care about the second, the third, or the fourth quadrant where the x1, either x1 or x2 become negative number. So we remove the idea of using this the following three sets of the solution from our consideration because it contains negative number. Okay. And then we move to case C. Case C, I think we start with the green. We start with beta 1 and G2, G1, beta 2 and G1, B0. And with that, we obtain x1, x2 look good. Our solution obtained is positive number. That's good, right? Because it's in the first quadrant. And beta 1 is 0.05. G2 is 0.14. And this is the only thing that we are not happy with, this one, right? I'm sorry. Is this one. Because of the G function need to be less than 0, but this one is not. It's 0.14 is positive. So it's not satisfy the condition, inequality constraint we have. Case D. Case D is the case where you see we have the two set of the solution. The first one is look good, right? I'm sorry, we start with it. Let me draw you first. We start with G1 and G2, set both of them to be 0, and then we obtain X1, X2, beta 1, beta 2 as the result. The first set of the solution is look quite okay, except you see there is the negative number here. X2 is the contain minus sign. This is negative number, and we discussed about this. We don't care about this is what it in the y is negative. It could be something like the the fourth quadrant, and we are not care about that. So we remove this from our consideration, right? It seems the only last set of the solutions look good to us. It looks like x and x1 and x2, both of them are a positive number. This is good. Beta 1 and beta 2, let me discuss about this later. G1 and G2 are always both of them 0. So it's good. Everything's good. So we check the area when x1 equal to 0.815, x2 equal to 0.913, we found the area of the rectangular inside this, inequality constraint is ellipse, and the straight line is equal to 0.744. That may be the biggest area or largest area that we can achieve with this problem. Yeah, and I hope in this world, no one can find any rectangular larger than this, right? This is the largest area in the world. Okay, so mathematically, this is the explanation through the equations, inequality conditions, and the way we considering the solution we obtain from the case A, B, C, D. But physically, I would say you need to link the mathematics with your understanding of physical understanding. This is very, very important. I think one of the things that I would like to discuss about this problem is about how to interpret this one into the physical feeling or understanding. Let me do you a little bit on the curve. Remove this, remove that. The blue is not, okay. See, it seems the solution we obtain here, the largest area could be the blue rectangular. The point that provide the maximum area in this particular case, I would say particular case is on the intersection between the linear curve and the ellipse function, I mean the red and the green. Some cases in the case, let me draw you the idea about this. Case A and B. Case A is trivial, right? X1, X2, 0, so I'm skipped. Look at case B. Case B that there seems one possible solution on the first set of the obtained solution where we have X1. I'm talking about this. Maybe I put the green color for you. You see, this is, I put the number 1, right? The green. X1 equal to 1.4, X2 equal to 0.7. Look at the area. The area is -1. The area is 1. 1 is greater than the solution we said before, right? 0.744. This is larger area. But why don't this solution be the maximum area that we should answer. This is because you see, look at G1. The G1 said the result is 8.989. This is a positive number. The meaning of this is what? The meaning is you violate the condition G1. If you trust this solution, you will violate the condition G1. But on the same time, you look at the G2, you see G2 returns 0. 0 means what? It's on the curve. If G2 return me a negative number, I would say that your point or your location of x1, x2 that you are considering is within the curve, below the curve, but not touch the curve, or not on the curve, not on the line. This is about the negative number. But when you say 0 is on the curve, exactly on the curve. So from this, I would have the idea like this. It's on the curve of G2, right? But violate G1. It's on the curve G2, but violate G1. Maybe the solution that this one provide, let me draw you with the green color. I expect to have 1.4 allow here, maybe. Let's certify it on G2. No doubt, it's on the curve of G2. But you see, you can have larger area, no doubt. This one is larger. The area, I don't know, the scaling, my scaling is good or bad, but look at the value, right? We obtained from the solution that we just obtained. The area below is of this rectangular is equal to 1. But the area of the solution of the blue rectangular that we said is the best or largest one in this world is just 0.7. So the green is larger, in fact. However, you see, it's violate G1 because it's beyond the curve, the linear line of G1, right? It's go outside the area allowed, feasible regions allowed by the G1 function. Therefore, this is not accepted. It is not accepted for the solution, of course. Look at other case, which one that we have a positive together, x1 and x2. Why don't we look at the case C? Let me draw you with the pink. We are talking about case C, number 2. It look good again when we look at the first quadrant and we have x1 and x2 both positive number. However, in this case, it look like if we look at the G1 and G2, G1 is 0. No doubt, it's on the line. It's on the line, a linear function. How about the G2? G2, we have 0.14. Unluckily, this G2 return a little bit positive number. But this is not allowed by our inequality constraint. We try to constrain ourselves to be a negative number for both G1 and G2, and therefore, this is not allowed, right? For sure. It looks like x1 is equal to 0.75, x2 equal to 1. Why don't we draw it on the curve using the pink color? Using the pink color, I forgot. Where is it? x1. x1 is 7.5 and 1. Okay. Then for 7.5 and 1 is here. I think it's just a little bit here, close to here maybe. Something like this. It's on the curve of G1, but it's a little bit above G2, right? And this is the case where we are not allowed again. Look at the area. However, if you look at the area in this case, is 0.75, which is just a little bit greater than the solution we just obtained, right? 0.744. We would happy if this is gonna be our solution because the area is a little bit larger, but unluckily it's violated G2 a little bit as well, right? Where you see G2 is a positive number 0.14. This is not allowed by our constraint. So this one is quite a good candidate, but it looks like it's not the best and it's not accepted by the condition we provide because it's violate the curve of G2, right? It's beyond the ellipse, the clean ellipse curve, and therefore it's not allowed by this solution. Okay, I hope you might feel a little bit about what we are doing. However, there's one thing that I would like to discuss a little bit about the Lagrange multipliers, the beta, what is the physical meaning of them? And also maybe I would like to quiz you on this. I have an idea about the quiz already, just a very simple. And I would like you to look at beta 1 and beta 2 now. Beta 1 and beta 2, both of them actually come from the function like this, right? The Lagrange multipliers, the penalty terms. And it looked like that the beta 1 and beta 2 seem to be a thing that have the can have a zero, can have a positive number, can have a negative number, right? In terms of mathematics, it can be any real number. However, let me go back to the curve. We have learned about a little bit about the lambda. It's the same thing with beta now. Lambda is the Lagrange multiplier and it's connected with the something like this, right? If I remember it's correctly. Is the change of the objective function with respect to the coefficient of the constraint if you have the equality constraint. If you put your consideration on the curve on the line, satisfy the constraint set equal to 0, okay, not below, not beyond the curve. This is the case where you look at the B exactly on the curve. And the change of the B with respect, the change of the objective function with respect to the change of the B coefficient of each lambda. Okay, of course, I'm sorry, you have many lambda, you have many beta, and you have many B if you have many constraints. It looks like this. For this one, what is your feeling? The line and the red line, right? The linear line, the red, and the green curve, the ellipse. If I increase B, would the area increase? Or if I reduce B, for example, look at this one. Where is my B? B is here. This is B1 and this is B2. Actually, if I draw this one as the BI and BJ, BI number, it could be something like this, right? 20x1 plus 15x2. Previously, we said this equal to BI or minus or subtract or minus BI equal to 0. This comes from equality constraint case. right? So the B1 is equal to 30, no doubt. How about B2? B2 is similarly is something like this, right? Over 4 plus x2 square equal to 1. And 1 is my B2. How about this? If this area is, how to say, if you ask me, okay, teacher, you can have the area or the land. I put the line curve like this. I put the line like this, G1, and I put the curve G2 like this. And if you can draw any area inside these two functions, I provide you this area. I provide you this land. And of course, I will try to maximize my profit, right? To get the largest area or land area as much as possible. And this is my solution. You see at the intersection point between the line and the curve. However, if you ask me again, if I have chance to select another one by changing the line and the curve. For example, if I change the number BI from 30 to 28, how it affect the area, the largest area I can have? Or on the other hand, if I increase the number BI for you from 30 to 31, 32, what's gonna happen? A similar question can be like, okay, not the line. The line is fixed. I don't allow you to move the line, but I allow you to move the curve, the ellipse. You have two choices. If I change the B2 from 1, right? On the left hand side, on the right hand side, B1, B2 now is equal to 1, right? If you have two choice, the first choice you change to 0.8 and the second choice is 1.2. Which one you like? It's easy to explain you now because the thing is well drawn on the curve, on the drawing. You can draw the thing, right? So it's easy to make yourself understandable. But in reality, in real problems, sometimes, somehow, you have many variables. You have many constraints. And important is you cannot draw the curve. You cannot draw the thing. You can imagine, I don't know, in the air. Remember, if you have x1, x2, x3, x4, how to draw it? How can one put 4 variables together on the page of paper, a piece of paper? How can? So that difficulties make engineer, when you look at your problem and you have to really understand, you can have a good imaginary. Okay, what would I deal with this BI? What would I should deal with this inequality constraint in a with a certain common sense? Like this, it's quite easy, right? To answer you how to increase or reduce the BI. So let me ask you as the quiz. I will have 3 questions for you in the quiz. And let me just use your understanding, or maybe you better draw the curve if you want, but I think it's be easy, a little bit not so difficult, very easy. And I hope all of you can do this job. Okay, I will have 3 questions. The first one is about if I I will ask you which action will increase the area, okay? And the first action, maybe I would say I increase the B1 from 30 to 30.5. The second action, I said that I will change my B2 from 1 to maybe 1.5. And the third action, I will ask you if both of them increase the area, if I have, okay, if I have a chance to increase or reduce the BI by 0.5, which action you will select, which action you will perform, okay? Understand what I mean? Okay, I will try to write down my Padlet within maybe a minute and send you the link. And you please think about these three questions. I will ask you about these three questions, okay? About the increase the area. Objective is to increase the area. Join the So you please think about this. I try to provide the link for you. I'm sorry, I just see the chat said about please explain.
Recording in progress.
I'm sorry. Why, why the x1 and x2 cannot be negative? We don't accept, okay. I said before that we focus on just the first quadrant, right? So both x1 and x2 is a positive number. Actually, x1 and x2 can be negative if you consider the second quadrant, the third, and the fourth. But I think for this example, we focus only the first quadrant where both of them, x1 and x2, need to be a positive number. That's why we discard or not accept the negative value of x. Okay, let me do the Padlet. It's quite difficult. Share. Okay, I think I just sent you in the chat, the Zoom chat about the Padlet link, so that please connect and answer me these questions. Okay, there's three questions. The first question, okay, the question is, I ask you, which action can increase the area? Question one, if I set B1 equal to 30.5, if you agree, you just say, okay, number one, say yes. If you disagree, you just say no. One equal to no, one equal to yes, for example, like that. Question number two, B2 equal to 1.5. If you agree, you say yes. You disagree, you just say no. And the last one, I said select the best action with 0.05, I'm sorry, with plus minus 0.5. It means you can just provide me on the third question. The solution is number three. You said you will change B1 to 30.5, or maybe you change beta one. So I'm sorry, B1 to 29.5, or you select the change on B2 instead of B1. You think it's better? You say, okay, let me select B2 equal to 0.5 by subtract of 0.5, right, from 1 to 1.5, something like this. Hope you understand my question, and please return me the solution. This one is not so difficult, so I think within just a couple minutes should be okay, like 2 minutes. So you have times of 2 minutes from now. Please hurry up. Don't forget to write down first your ID, right? And following with the solution. Okay, maybe I will put example for you how to write down the solution back to me. Let me try to. Okay, if I said number one, yes. Number two, no. Number three, okay, look at the pattern, right? Please try to answer in this fashion. Your ID and then your solution, three solution. Yes, no, no, yes, and the best action. And when you said the best action, you have to look at B. I need B1 or B2. Don't say BI, and don't say just put plus 0.5 is not, is wrong. The answer like that is not acceptable. You should edit it. And if you said you select B1, you need to show me B1 is 29.5 or 30.5, which one you like. You have to select one of them. Don't just say B1 and say both is not okay for me. If you would like to say both, I need the direction. You say B1 need to be 29.5 and B2 need to be something like 0.5. Both of them are equal. Earlier, if you want to answer like that, say so. Don't put the wording like both. Both is not acceptable to me. You have to edit your solution. Some of you say that. Okay, I got 7 answer from all of you, 9 now. Hurry up. Okay, 1 minute more. Okay, 20 seconds. Okay. I got 25 answer now. 10 seconds. Okay, time's up. So I will close the link. Let me see the answer from all of you first. It look like Mhm. Mhm. The first question, many people say yes. The second question, many say yes, some say no. And the third question, some put on B1, some put on B2. It's not consensus of you say quite different. Okay, this is good. It's a democracy world, right? You can have different idea, but it's not good for the mathematics and engineering since our solution is only one and unique. Let me explain a little bit on this again so that you can maybe can follow up and have the more clear understanding. For sure, this one increase B1 and B2 will increase the area. Why I can say so? You can draw the curve. You can draw the line yourself. If you change the number from 30 to 31, what's gonna happen for the ellipse? I'm sorry, for the linear line T1, it will shift a little bit, right, to the right-hand side. And similarly for the green ellipse, G2, this curve, if I change from 1 to 1.5, it's larger. I mean, the ellipse is bigger. And if I reduce from 1 to 0.5, the ellipse is smaller. So the direction where I will improve G1 and G2 to maximize the rectangular area inside, I would say that I will increase both of that. Look at the drawing. I will feel like that. But look at the drawing itself. I cannot have a clear idea which one is better. Increase G1 or increase G2. Which one will provide a better rectangular, inside rectangular area that I would get? By drawing a curve, I have no idea about this. But I need to look at the mathematics. It will be the tool that help me to consider this. Mathematics of this is about the beta. There's the beta here. See here, you have as the solution, you have beta 1, 0.044. You have beta 2, 0.086. So with these two betas, it explains something to me. It said, okay, if I increase or I change the BI of B1, the rate of change of B1, that will affect on the objective function is about 0.044. And similarly for the rate of change of the objective functions, that means the area of rectangular inside, will be 0.086 for G2 or B2. See, if I have the chance to, how do you say, change B1 and B2 with the same rate, with the same amount, I think it's much better to push on G number 2 of B2. In other words, I will use the B number 2 change from 30, I'm sorry, not 30, right? From 1, B number 2, yeah, from 1 to 1.5. You understand? Because the beta 2 tell me so. Beta 2 is 2 times faster or larger than beta 1. And that will make me to trust the mathematics, because the curve, from the curve is very difficult to fill this. I need mathematics, a number to support my decision. Okay. Hope you'll be able to link between the mathematics with the real application as much as possible. I don't know. I try to, but it's sometimes it's very difficult. Sometimes it's natural to link these two worlds together. But trust me and believe me about this. I don't think the good mathematicians can do the best engineering job. Mathematicians is good at solving the thing, solving the problems. Of course, I agree. But they have just the number. Mathematics is just the tool. You have a good, or you have the very best tool, very good calculator with you, but you cannot use it. Your calculators have no power, no battery. It's not good, right? Even though you can solve this solution, provide me the solution, exactly what I want or what is the exact solution is, of course, it's good on mathematics. You're good at. But this subject is for engineers. You and me are engineers. So we don't learn mathematics itself. We learn what we call the applied mathematics, right? We would like you to be able to apply them and use the mathematics as the tool. Okay, we have to learn how to use a calculator, the same thing. I have to learn what is the optimization in terms of mathematics to understand the calculator. And after I myself understand my calculator, I understand what is the optimization is in terms of mathematics. What is the necessary condition? What is the sufficient condition? How to classify the stationary point using the sufficient condition, like using the Hessian matrix, using the Baudelaire Hessians. Beyond that, it's gonna be engineering. You have to connect this mathematics with your application as much as possible. Okay, let me move to a further discussion. I try to make the chapter short as much as possible so that we can have enough time to discuss the next chapter about the differential equation, right? Numerical technique for that. Well, this one is about the application. Okay, this one is good. I think this example is good because it's already provide you the connections to show you the connections between the mathematics and the real world now. Especially for the structural engineering applications. This is the two examples I selected from the text for you to show you how we can apply the optimization to the real world to design your structural members. And maybe, I don't know, this one is a loop truss, maybe the bridge. You can imagine about that. Okay, please look at example number 1. This example is just a symmetric statically determinate truss structure. Okay, you can see in the figure, this is just the truss that we have learned in the undergraduate level. So it's quite easy, right, to analyze if this truss is a determinate structure. For this truss, the idea is not asking you just to analyze the forces, the internal forces, reaction forces, and decide the member according to the force like that. We have learned a lot about this in undergraduate, and in the master level, I don't think quite interested to do so. You have a many commercial program to provide you the section of the trust, the steel grade, the capacity, your design is good or bad, safe or not. But in this example, we will look at a more precise real world where the engineer would like to design this truss with the cheapest one, the minimum weight. If I ask you to do this one, this problem, without the knowledge of optimization, I believe is very, very difficult. Since what you're gonna do, I expect, is to draw many truss and try to compare the weight of your desired truss. Maybe you try to compare 10 of the truss structures and which one is the minimum weight. Okay, it's not, believe me, it's not easy. My feeling is, okay, you fix me the length 2L, right? You have L here, you have another L there, the lower. Why don't we have the truss like this to carry the point load P like that? Why don't we have just a rectangular H1? You look at the figure, small H1 and H2, both of them are equal, and it's like this. We have seen this in many loop structure, in many steel truss bridge for the railways, for the highway. The idea is like this. Many engineers use this, but I will show you. I can show you with this example. That idea is not the cheapest one. You will use the we're gonna use the mathematics using the optimizations and see what gonna be the minimum weight of this type of configuration of the truss. And I believe no other engineers can do a better truss than this, because this proved by mathematics. It's a lowest weight, okay, available to this world, unless you provide me another constraint or you provide me another condition of the design of the truss. Maybe the solution would change. But if the set of the constraint we provide and the condition we provide for this problem is the same, at this example, I believe this solution is the best in the world. Okay, let me try to. This truss is the determinate truss structure. And see, we would like to obtain what's gonna be the minimum weight. And in many cases, if your truss contain minimum weight, it means this truss is the cheapest as well. It's implied, because when we try to buy the steel member, they ask us about the weight. The cost of the steel is depend on the weight, not the volume. Actually, the volume and the weight is the same because the density is fixed, right? But not the length, but not the other dimension. It's about the weight. They will ask you about the weight, and that will compute the cost. So in other words, this question is try to minimize the cost as well, even though they say the weight. Before we write down the objective function, I think the objective function would something like let me turn off my telephone a bit. Okay, let's continue. to make it fast, maybe I will go from the equations one by one, maybe. Okay, the concept is I have to write down the objective function, right? And then from that objective function, I have to apply the necessary condition and follow up with the sufficient condition and confirm that the solution I obtained from the necessary condition is still a real or local or global minimum value, something like that. It could be such kind of protocol or procedure to obtain the solution for the optimization. But in this example, you see they start with the internal forces. They first try to compute. This one is a structural analysis, so I will skip. It's not so difficult for you to self-understand about this, right? You start with the reaction like this, take a moment at the support, and then you will go through, okay, this member, I think the force is going to be 0. The same thing for the lower chord of this truss, since the force P is just here, this point, right? So the internal force, this one, F number 2, is gonna be compression force. Let's say compression is a plus or minus. Let me show. Minus here. It's compression P over 2, right? And from this, I believe that you can have the equilibriums. I'm sorry, if it's a compression, I can have to draw the thing like this, and I assume it's a tension in number 4 and number 5, and with the F4 and F5 is in equilibrium at this node, right? This joint. Therefore, you have to take the equilibriums of the horizontal force and the vertical force, and with this equilibrium of the two components, you have the two unknown F5, F4 and F5. So I believe that you can get the solution of the internal force F4 and F5 without any difficulty. And believe if this example is correct, you would get something like the F4 equal to this amount, F5 equal to that amount. And from that, I think you can look at this one, F5, F5, and then in equilibrium of F number 1, something like this, right? If you look at the top joint or node, and then you obtain F1 as the internal force. The next step is about the, okay, look at the internal force. The internal force is just the determinate number. Now is become the function of the value is depend on the H1 and H2 as the variable, design variable for our optimization problem, right? This is the two unknown for us, H1 and H2. Let me use another color for you. This is the primary unknown for these optimization problems. And then we put, and we say that if we want to make the thing lightest, mean the minimum weight, what I gonna do is to fully stress all the members. And to do so, what I have to do is to divide the force with the allowable stress, allowable strength that provided by the design code, right, for the steel member. And let's assume that in this case, both tension and compression, both of them subjected to the same allowable stress, sigma 0. Therefore, the area, the minimum area that will satisfy the strength of the member is equal to the magnitude of the force Fi divided by the sigma 0 as in equation 2.1.5. You do this for every member. So from member 1 to member, I don't know, 1, 2, 3, 4, 5. Okay, number 3 maybe is not so, since the force is 0, it's not affect our solution or our design, because you can set just the constant minimum section for the L number 3, right? But for the number 2, number 4, number 1, and number 5, you have to set that the stress is not greater than allowable stress. And this is what we have done here in 2.1.5, and you obtain the area for each member from the force, from the internal force. And when I have the area, if I want to find the weight, I need to compute the volumes. To compute the volume, the volume is A multiplied with L, right? Let me use small L for each member. I don't know. Otherwise, you will confuse. Okay. Let me try with a small L. The length of each member. You multiply the area with the length, you got the volume. And this volume, when I multiply with the density, what I get is the weight. So minimizing the volume is exactly the same with minimizing the weight of the truss. Therefore, 2.1.6 can be your objective function now. The volume function V equal to 2. Well, of course, we introduce the AI, we introduce the Li of every member. Altogether, sum them up. You got 2.1.6 as the 2 multiplied with P over the sigma 0, or multiply with H1 minus H2 plus H2 square over H1 plus L square over H1. This is volume functions. And it can be the objective function as well. So our objective function now, I think you can write down the objective function is something like the volume function V of H1 and H2. Remember, H1 and H2 is our unknown. Something like this, right? And you try to minimize this. Minimize V. This is our objective function. And I put no constraint, no other conditions that will take into account. For example, I don't care the deflection, I don't care the deformations. What I do care is about the strength. And I guarantee you that every member will be able to carry the load with allowable stress, not greater than the allowable stress. Actually, it's exactly equal to allowable stress in every member, right? This is what we define for, we calculate for the cross-sectional area before. So if this is the case, this is the case of what? The case of the multiple variable optimization without any constraint. Hello, everyone still hear me?
Yes, yeah.
I'm sorry. I think my internet connections. Hello again. Can you still hear me?
Yeah, Ajahn.
Thanks. Okay. Sorry for this internet problems. It could be okay now. Yeah. Let me continue. I think we are, before I lost, we on 2.1.6. Am I correct? No? If you don't say anything, okay, let me continue. Is the we set the objective function v, right, the volume, and try to minimize this volume. And the necessary condition is 2.1.7 with respect to H1 and H2, you obtain the function, the equation like this. And of course, if you want to get the solution, you need to find what is the stationary point. In this case, I believe that since the H contain power 2 in these equations, I expect to have at least two sets of the solution. Maybe you have 4 or 5, I'm sorry, 2 or 4 as the solutions. However, I think the remaining 3 maybe is within the second quadrant, the third quadrant, and the fourth quadrant, where you contain negative number for either H1 or H2, therefore is not how to say, it's not considering in our problem, right? It's trivial. Therefore, the only solutions, stationary points in the first quadrant is allowed here, and it's become 2.1.8. You look at the 2.1.8, it's very interesting, where you see the value of H1 and H2, both of them not constant. I'm sorry, not equal to each other. The value of the H1 star and H2 star is look like at the middle, the midspan, the H is two times longer. The in term H is the height of the member, right? The height of the vertical member at the midspan is 2 times higher or longer, I mean, in terms of length, than the vertical member at the support. And vertical member at the support is only not 1/3, 1 of the square root 3. This is about 0.5 something, right? I don't know, 1 over square root 3. Let me try to compute this. I want to see the order. Yeah, 0.58. About 58 or 60% of the length out. Okay, 60% of the length out gonna be the vertical member of the supporting truss. We are looking this. It seems like this one is 0.58 of L. Could be the good one, the good shape, the best shape to provide the optimum solution. And at the vertical, you have 2 times height, right? So it's gonna be 1.66. About 1.16, sorry, 1.16 L in terms of length. So this actually the solution, but we have to go further to confirm this solution is the best one. To do so, we will start with introducing H1 and H2 equal to H1 star and H2 star, right, into the Hessians. But in this step, they just show you that if you set the height of H1 and H2 equal to 2.18, as in equation 2.18, the area gonna be 2.19. And the interesting is the area of this member, you see, A1, A2, A4, A5, all of them have the same area. It means what? It means I can buy the trust with the same member. This is very, very cool. Since when I buy the still member, if I change the sizing, if I change the area, it's not provide in the market, right? Some section is not available. It's just a fixed area in the market when we have the still table that the shop steel manufacturer provide you. So in this case, it's implied what? It's implied that I can have the same section for all member, and that is very, very practical. Solution is 2.19. And if you go further for the Hessians to make approve to show everyone that your obtained solution is real or local or global minimum point. To do so, I have to perform one more derivative, right? So this one is the sufficient condition. With the sufficient condition, we have to perform the second derivative of the objective function with respect to hi and hj. In this case, you have h1 and h2 as only two variables. So the Hessian become a 2 by 2 matrix. And this 2.1.10 show you about that. I have to introduce or evaluate the optimum value at the H1 star and H2 star. Therefore, I have to introduce into the 2.1.10 with the 2.1.8. I think you introduce 2.1.8 into, you obtain 2.1.11. This is a Hessian star. This is a evaluated at the solution 2.1.8 locations. See, when we introduce the solution H1 and H2 star back into the Hessian matrix, the Hessian matrix become just a constant matrix, contain only the constant parameters and the number. And we have to prove this, to check this, whether this one is a positive definite matrix or not. You have the two choices of the check, right? One is using the leading principal minor, which very easy now, right? The leading number one is 1. The leading number 2 is what? H1 equal to 1, right? H2 equal to what? Equal to, I'm sorry, 1/4 plus, then the minus, and then plus 1. So you got something like a plus, something like this, right? This is, I remove the coefficient. I just look at the matrix element. And this show me that this is a all positive number. The leading principal minor of the Hessian is a all positive number. So this matrix is a positive definite matrix. Okay. And for sure, positive definite matrix. And thereby they say, thereby providing the sufficient condition of the optimality of the design. Mean what? Mean your objective function, your solution here is a true optimum. It's not just a center point. It's the minimum weight. And I believe this is not, this is the best one in the world where you cannot find any other trust having smaller weight than this. So the solution is look like, if this L, I could have something like this, 60% here, and 1% is there. So as the solution is look like, this is the best trust in the world, contain minimum weight to carry the point load P at the middle. And I cannot find better trust than this, right? With this one, you see, as an engineer, it's very difficult without the optimization tools like this to help us to get the trust that the cheapest one Without them, maybe we need to design many trusts and compare which one is the cheaper or cheapest among the design trusts we have in hand. But with the optimizations, see, you can find what is the best. Just knowing how to use this tool, knowing how to use the optimizations, and you apply it to your problems, you get the best trust in the world. No one can beat you. No one can find a better trust than you, with a certain condition, of course. So this show you, I think, about the use of optimization applied to structural design. It's very simple example with the small trust. But of course, when you're dealing with the real trust, the real member, and you have many members, maybe you have to use a numerical technique, and we will discuss about that later. But you see the idea, right? That we can apply the optimization to our problems. And it seems work. One more thing here that I would like to address is about the convexity and concavity. You look at these problems, see the Hessians. The Hessians is a function of the variables. It contains the term h1 power 3, h2 power 2, something like this. Many terms, many parameters. So for sure, this kind of Hessians is not the convex function nor the concave function, right? It cannot be the convex function and concave function whenever, if and only if I can show you the 2.1.10, 2.1.10, not 2.1.11, 2.1.10 is, to say, the leading principal minor of them, always positive number, independent from H1 and H2. So I'm doubt whether I can do so with 2.1.10 or not. But my feeling is I cannot. So I believe, you don't trust me this. I never proved this. I just look at the Hessians and feel that it depends on the value of H1 and H2. So sometimes if I introduce H1 equal to this number, to that number, maybe it's gonna be a negative, how to say, negative leading principal minor my occur. Therefore, I cannot conclude that the from 2.1.10 is the convex functions. However, we can do the test by introduce, right, 2.1.8, introduce the H star into this 2.1.10 and obtain 2.1.11. And once we introduce the stationary points, the term of H1 and H2 will remove and replaced by the value of the number. And it's become the constant matrix. And with the constant matrix, it's easy to get check the principal minors, right? And this one we prove and show you already that this leading principal minor is all positive number. So our conclusion is just a local minimum. I'm a little bit afraid that there might be someone can find a better trust than this, because this one is just proof and guarantee the local minimum. If there is a guy who is very good in mathematics and engineering come to attach this problem, what they have to do is like this. They have to thinking about a new objective function V. The new objective function V, the volume, they need to find another function, not the volume directly, but maybe a variation of the volumes in such a sense that is implied the volume is implied the weight, but not 2.1.6. Because 2.1.6 is not a convex function. I think it's not, but you can test yourself. You have to find another objective functions that can imply the same target or same objectives while the weight of the thrust, the whole thrust, but have to write down this equation carefully so that is a convex function. If you can do that, I'm doubt the solution 2.1.8 might change or not. If you can change the 2.1.8 to the new stationary point based on the new objective function, maybe that is the global minimum. That's gonna be the global minimum, right? Because your function, your objective function is a convex function. A convex function guarantee that is only one optimum point or one minimum point, and that is become the global minimum for sure. Okay, I'm sorry about that because I cannot find what is the convex function for this problem. I cannot provide you the objective function has the property of the convexity here for you and leave this to you. The idea is like this, but I'm not good at mathematics. Therefore, I cannot imagine what's gonna be the objective function, the new objective function that has become a convex function. That will be very, very cool where the engineer in this world cannot compete with you. They're gonna be the global minimum. But this one is good, right? You obtain the very good solution already, but you cannot say global yet. That's it. And going back to this, you see, with this one, with this optimization, we can have the thrust, the base shape of the thrust, H1 equal to 0.8 L, H2, H2 equal to 0.8 L, and H1 equal to 1.16 L. And this will make your thrust minimum weight. I cannot have this kind of the clean thrust without the optimization. With my just experience, what I feel is I use a flat, right? Flat thrust, like H1 and H2 are equal quite often. And I found maybe this one could be the best. Actually, it's not. Okay, let me move a little bit. Oh, it's 10:30. Why don't I stop here? And next time I will finish this chapter about the optimization. This is, okay, we have, this is about the numerical techniques mainly. So it's very fast. Let me finish this one. It will take you 10 minutes. I will not take longer than that. Just brief the idea behind, because this example is well written in the textbook. You can find this textbook and self-study. Consider one more thrust. And this example number 2, I think the idea is the thrust is given by the configuration as you see. The length of each member, I think is L, is equal length. And I think the force is given by P1, P2, and P3. Okay, so this is the thrust, and of course, under the loading, they will move, have the deformations. The idea is rather the same as before. I think they would like us to minimize the total volume of the material used for the whole thrust members. And the only thing that different is they don't care about the stresses now, but what they care is about the deflections. If this thrust is part of my, how to say, bridge, highway bridge, Maybe you're talking about the length out here. If you're using for the, I don't know, the Astro standard, but for the highway, I believe the delta need to be less than L over something like 800, something like this, right? Maybe it's depend on the design code. But for example, if my bridge is contain only the traffic of the vehicle, not the pedestrian. When I say pedestrian, mean I cannot walk on the bridge. Only the cars and the trucks can cross over. In this case, we do not care much about the vibration and the diffraction. Maybe the L over 500 could be enough for that. Okay, you can check with the design code. This is just the idea. I would like to briefly provide you what the problems related with the real application is. The second is if I have the pedestrian, I have a people like we have the walkway, pedestrian walkway on the bridge as well. Not only the trucks and car will fly over, but we have also the people who walk on the bridge. Then we will talking about the diffraction limit of the delta less than maybe L over 800. This is the example for the highway problems. But if you're talking about the high-speed train, it's called the high-speed railways, HSR. The high-speed railway, maybe the delta set something maybe more stringent, more strict. It's like a L over 1, is you code, I think, 1,000 something. Maybe 1.4 thousand, so 1,400 or 1,800, 2,000 can be. It depends on the speed of the train, and it depends on if the train is carry only the passenger train, not the freight train. The freight train is a train carry the stuff, the goods, right? The materials like the oil, something like that to convey on the train, freight train. It depends on the situation as well, but the diffraction is very, very more strict that I have to design my bridge to have very small diffraction to guarantee that the comfort of the people in the high-speed train, you will feel nothing when you drive or lie on the train on my bridge. And in the same time, I have to guarantee that the stresses on the rails, the track, is not greater than a certain amount, and that will be controlled by the diffraction as well. To do so, I will try to minimize the weight of this thrust volume, right? And this is the only constraint we have. The idea they use a virtual work and get the diffraction as the function. You see 2.3.14. The delta is the function of the summations of the Fi, the small fi, big Fi, product of them over AIEI multiplied with Li, something like this, right? You can find in many textbooks the way of using the virtual work is quite easy from the undergrad study. We familiar with that, right? And then we calculate what gonna be the volume. The volume is AILI. So you see 2.3.5, you minimize the volume of AI. So the variable become area, cross-sectional area of each member called AI. And the volume is a summation of AILI. Li is the length of each member, right? And subjected to the equality constraint. This is our equality constraint that to provide from 2.3.14 to guarantee that the area you given to me will not allow to have a large diffraction than delta that given by the design code. Okay, and from that, if you want to do the optimizations, you have to perform what they call the Lagrangian, right? Using the Lagrangian, you have the Lagrangian functions of A and lambda. Lambda is a Lagrange multiplier, the penalty function, the penalty parameters. And it become 2.3.16. And see, you have to find necessary condition. And once you find the necessary condition is the curve L with respect to AI and curve L with respect to lambda. And this provide us 2.3, 0.17 and 2.3, 0.18. Okay. And solving for this, from equation 0.17 and 0.18, you can solve for AI and you can solve for lambda, I believe. And this is the solution after solving both equations. You obtain 2.3.19 for lambda. This is a lambda star, right? This is a stationary point already. And AI star equal to this amount. And without the proof of the sufficient condition, actually you need one more step, right? About the sufficient condition. But it seems that it's missing from this example. They just obtain the stationary points and believe this is the optimum value and trust this 2.3, 0.20 and compute the volume. And they say the minimum volume is gonna be this amount, 2.3.21. Okay. So you need to add the sufficient condition if you want to really prove that this volume is the local minimum or global minimum. Otherwise, you don't have a mathematical proof. You just believe that this should be, it should be the minimum value, right? And without any proof, maybe it's good, but it's not based and is not accepted in the subject of applied mathematics, right? Because we have to strictly with the mathematics and apply every step necessary to prove, to show that this is the optimum and this is the minimum, right? Without that, maybe we just believe, we just trust, we just expect, we just, how to say, it's an engineering sense because this is a stationary point and only one stationary point. The center might say, without any proof of sufficient condition, I feel this one could be the minimum point already. That's it. In engineering application, it depends on you. You are the engineer in charge who have to make a decision yourself. But in terms of mathematics, we need it, right, to prove the sufficient condition. That's a difference between the engineering and mathematician, I think, engineer and mathematicians. Okay, I would stop here. Next time I will come with a numerical searching technique for you, and maybe I need to install my MATLAB so that I can show you how it's worked. Okay, any questions so far? No? Okay. So I would like to stop here and thanks for your attention and believe to meet you next time, next week, right? Next Monday. Okay, have a good day and goodbye.
Thank you, Ajahn.
Thank you, bye.